We're going to take a look at problem 3 in the packet of particle motion examples. So take a moment and read through the statement of the problem and take a look at the graph that we have. In part A, I want to know when the speed is the greatest. Well, remember, speed is the absolute value of velocity. I have the graph of velocity, so the graph of the absolute value of velocity would be the same thing, but with everything flipped so it's above the x-axis. This would stay where it is, but this piece would get flipped up here, and that piece would stay. Well, I think the speed will then be the greatest at t equals 8. Because the velocity is -6 there, the speed would be +6, and all the other speeds are some value less than 6. So we're going to go with 8. Part B. When is the acceleration the greatest? Well, let me find the acceleration at those various times. The acceleration at time 2, the acceleration at time 6, the acceleration at time 9. Acceleration, remember, is just the derivative of velocity. So v prime of 2, v prime of 6, v prime of 9. We have the graph of velocity, so the derivative of velocity would just be the slope of the graph that we see. At time 2, the derivative of the graph that I see looks like 0. At time 6, the derivative of the graph that I see is, well, I could do a rise and run thing, but for right now, let me just say that it's something negative. And at time 9, the derivative, the slope of the graph that I see, is some positive value. Well, I can look at those 3 times and see that the acceleration is going to be the greatest at time 9 because that's the positive value and the other one was 0 and negative. So I'm going to say at t equals 9. And as for the explanation, well, the calculations that I have over there are fine for the explanation. Next, when is the particle moving to the left? Well, the particle's moving to the left when the velocity is less than 0, is something negative. I have the graph of velocity. I want to know when the velocity is negative, so I'm just going to look at my y values. I'm going to say between 4 and 10, and my justification is because the velocity is negative in that interval. Part D. Over what time intervals is the speed of the particle decreasing? And explain your answer. Well, the speed will be decreasing, or the particle is slowing down, when the velocity and acceleration have opposite signs. Let me write that down just so I kind of keep that in mind. When v of t and a of t have opposite signs. So I'm looking for where the values on the graph that I see have an opposite sign from the slopes on the graph that I see. I think that's going to happen between 2 and 4 because my velocity is positive while my acceleration, the slope of the velocity, derivative of the velocity, is negative. I also think that's going to happen between 8 and 10 because the velocity is negative there while the acceleration, the derivative of velocity, is positive. Well, let's take a look at the next page. In part E, we want to find the total distance traveled by the particle over that interval. Well, total distance is the integral from 0 to 11 of the absolute value of velocity. So really, I'm just going to go find the areas, and not even really signed areas, just areas because of the absolute value. I'm going to make them all positive. I see a semicircle over here with an area of 1/2 times pi times 2 squared, 1/2 times pi times 4, or 2 pi. I see a triangle over here with an area of 1/2 times 6, or 18. And then I see a triangle over here with an area of 1/2 times 1 times 3, or 3/2. My total distance will be 2 pi plus 3/2 plus 18. I can get a common denominator and add those things together, and I'm going to say 2 pi plus 39 over 2. That'll be the total distance traveled. In part B, I want to calculate that integral and explain what it means. Well, the integral of velocity, without absolute value bars around it, remember, means the displacement of the particle, the net change in position of the particle. So this time I will deal with signed area. I'm going to do 2 pi minus 18 this time, plus 3 halves. I can get a common denominator and subtract those things. I'm going to say 2 pi minus 33 halves. And this gives me the displacement of the particle, or the change in position. And I should probably be a little more specific, over the time interval between 0 and 11. Finally, if the initial position is 2, we want to find the position at time 11. Well, I can take my initial position of 2, and I can add my displacement to it. So 2 plus the integral from 0 to 11 of v of t dt. Well, I already know what that is. I calculated that in part F. So I'm just going to say 2 plus 2 pi minus 33 halves. And we're going to end up at a position of 2 pi minus 29 halves.